Welcome to Quantum Realms Explained, where we demystify the most intriguing concepts in quantum mechanics. Today, we delve into one of the most profound and often misunderstood pillars of quantum theory, Heisenberg's Uncertainty Principle. This principle doesn't just describe a limitation in our ability to measure, it reveals a fundamental truth about the universe at its smallest scales. It's a concept that challenges our classical intuition and opens up a world where certainty is a luxury, not a given. At its heart, the uncertainty principle states that there are certain pairs of physical properties of a particle, like its position and momentum, that cannot both be known with arbitrary precision simultaneously. The more precisely you measure one property, the less precisely you can know the other. It's a trade-off inherent in the quantum world. Let's break down what position and momentum mean in this context. In our everyday experience, we can measure both the location and the speed of an object with great accuracy. A car's position and speed can be known precisely at any given moment. But in the quantum realm, for particles like electrons, this isn't possible. The principle is expressed mathematically through an inequality, not an equality. It involves Planck's constant, a tiny but fundamental number in quantum mechanics. This constant signifies the scale at which quantum effects become significant. The tiny value of Planck's constant is why we don't notice the uncertainty principle in our macroscopic world. Its effects are only apparent at the atomic and subatomic levels. So why is this principle so important? Firstly, it's crucial to understand that this isn't a limitation of our measuring instruments. It's not that our tools aren't good enough to measure both precisely. Instead, it's an inherent property of nature itself. The act of measuring one property of a quantum particle fundamentally disturbs the other. The uncertainty principle has profound implications. It sets fundamental limits on the precision with which we can predict the behavior of particles, influencing fields like quantum computing, where the probabilistic nature of quantum states is harnessed. Consider the double-slit experiment. If you try to determine which slit an electron goes through, its position, its wave-like interference pattern disappears. If you don't, the wave pattern emerges, meaning you lose information about its precise path. While position and momentum are the most famous pair, the uncertainty principle applies to other complementary pairs of variables as well. For instance, there's an uncertainty relationship between energy and time. The more precisely you measure the energy of a system, the less precisely you can define the time over which that energy existed. This means that particles can momentarily borrow energy from the vacuum, as long as they pay it back within a very short, uncertain time frame, leading to phenomena like virtual particles. In conclusion, Heisenberg's uncertainty principle is a cornerstone of quantum mechanics, demonstrating that the universe, at its most fundamental level, operates on probabilities and intrinsic limits rather than absolute certainties. It's a powerful reminder of the mysterious and beautiful nature of reality, constantly inviting us to explore further into the quantum realms.